Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to be part 3 of a 3-video series here on calculating torque about a point. So what we're looking at here is we've got this object, this beam here, that makes a 36-degree angle with the horizontal. This video I'm going to do a little more generically without numerical values. I've got 4 force vectors shown on it, a force vector F1 up, F2, F3, F4. We're going to assume that F3 acts at the geometric center of this object. And what we're going to do is we're going to calculate the net torque about this point. Now, the only reason why I'm choosing that point is because you'll notice that both of these force vectors go through this green point here. F1 goes through that point and F2 goes through that point. It is very common when you're doing a free body diagram and writing Newton's second law equations to want to choose points that are kind of advantageous. So when you draw a free body and you're trying to write a torque equation, it's very common to look for points where you have multiple forces going through, because when you identify a point like that, these two forces will not produce any torque about that point, and you end up with a relatively simple equation. So I'm going to go ahead and choose that point. And what I'm going to do is try to calculate the net torque about that point. Again, I'll just put net torque about the green dot. So as we do that, we say, all right, I'm going to start with this force vector right here. F1 basically goes through the green dot, no torque, so I'm going to put 0 for that. F2 also goes through the green dot, so I'm going to put another 0 for that. And the first force vector we run across here that's going to produce any torque at all is F3. Now, F3 is at a distance which is half the length of this beam. That was my intention, was that the F3 goes through the center of this beam. This beam, we're not given a length here, and I did this fairly intentionally. I hear this all the time with students. They tend to say, oh, I don't know a value, so I'm going to stop now. Well, this beam, if it doesn't have a length label, that doesn't mean it doesn't have a length at all. It does have some sort of length. We can observe that in the picture. So what I'm going to do here is I am going to give that length a name. I'm going to call the distance from here to here L for the length of the beam. I know that this number does exist. Now, the force vector F3, it does not make a right angle with this distance. The hypotenuse here of this triangle would be L over 2. So this distance right here is half the length, but that distance does not make a right angle with that force vector. There's a couple ways we can handle that. Method number 1. We could take this force vector and break it into components that are maybe like this and like this. This component does make a right angle to that distance, L over 2. This component is parallel, so we could take this force component times this distance. Now that's what I did in the previous video. So in this video, I'm going to handle that in a slightly different way. The other thing we can do is look at the line of action of F3. F3 acts all along this line. The distance from this dot that makes a right angle to the line of action is this distance right there. See how the line of action and that distance make a right angle. This distance is fairly easily calculated from this geometric triangle right here. The hypotenuse of that triangle is the distance from here to here. That is half the length. Therefore, that distance is L over 2 times the cosine of 36 degrees. That's coming from the fact that cosine 36 would equal the side adjacent divided by the hypotenuse. So when we calculate the torque for F3, we can do F3, whoops, and I put a 2, I called that 3, F3, whatever that force is, times the distance, L over 2 cosine 30. Now you notice I've already put the minus sign in. I'm sticking to my standard counterclockwise positive, and the force vector F3 is making this beam want to rotate clockwise about the green dot. Hence the torque term would be negative. So this force is now taken care of. All right, now let's move on and take a look at force vector F4 here. So force vector F4, again, the angle between that force vector and the distance L is not 90 degrees. So again, I could break this thing into components, but instead what I'm going to do is I'm going to look at its line of action. Its line of action is all along this line. The distance from my green dot to this thing's line of action that does make a right angle is this distance here. See how that distance makes a right angle to the line of action. And this angle is 36 degrees. That makes this one 36 degrees as well. And from this geometric triangle right here, and the hypotenuse of that triangle equaling the length of this object, that distance is equal to the L, whatever that length is, times the sine of 36 degrees. So when we calculate a torque for force vector F4 here, I'm just going to take the force F4 and multiply it by L sine, sine 36. If I'm going to shorthand my trig, I should shorthand it everywhere. So again, this reads F4 times L sine 36. This force vector is making this beam want to rotate counterclockwise about my green dot, therefore that torque term is positive. So the purpose of this video is to demonstrate how to calculate a torque term by finding the perpendicular distance to the line of action of the force, which I've done twice here. I hope that this video has helped demonstrate that for you. Have a great day.